Hello, welcome to Chapter 20, Air Heater Leakage. Air heater leakage is a little understood topic, and hundreds of operators that I've taught my combustion class to, not one operator knew what the air heater leakage was on his plant. And yet, air heaters are quite important. Here are 4 topics that I believe could be important to power plant management. Load, what's the full load and minimum loads? D rates and the availability of the unit, the efficiency and heat rate of the unit, and of course, maintaining the unit within pollution limits. So what are 4 things that air heater performance impacts? Well, it certainly impacts load. I can't tell you how many power plants I've been to that run out of ID fan, induced draft fan. How many power plants run out of ID fan in the summertime? And I'm like, do you think they designed it to be that way? Or maybe something's deteriorated? And more often than not, one of the important factors is that percent air heater leakage. Issues with air heaters and airflow can cause availability and D rates if you run out of air. The air heater provides approximately 10% of the efficiency on the boiler. In other words, taking that temperature from the economizer gas outlet temperature down to the precipitator or stack temperature, 300 degrees C down to 150 degrees C, or 700 degrees F down to 300 degrees F. That gas temperature drop through the air heater increases the boiler efficiency tremendously by lowering the stack or gas outlet temperature. A couple of important considerations is that a lot of slag experiences that I've had to deal with are a result of lack or limited amounts of air. So if you run out of air and you try to operate with lower O2s than maybe what you normally run at, you might be asking for slag to build up in the convection pass. If your fans are maxed out, just like if your pulverizer maxed out, if you're the control room operator, are you really in control if you've got something at the limit? Because really what you're saying is if you're up at the 100% limit, all you can do is go down. Sometimes when we're running high load and we starve the furnace from air, we actually see an increase in the furnace exit gas temperature, which again now points towards more slag in that convection pass reheater section of the boiler. And in numerous cases, I've seen that excess air heater leakage beyond the design is causing these issues. And keep in mind, of all the operations people I've talked to or taught classes to, virtually none or nobody knew what their air heater leakage was. I sometimes joke, just so you can remember how important this is, that air heater is like the choke point around a power plant. So just like you have to choke the chicken, those air heater and air heater leakage is like a choke point around the power plant. The concern is that the high pressure, high duct pressure FD fan air coming into the air heater leaks over to the low pressure and sometimes even negative pressure ID fan suction. And so because you have a very high pressure and low pressure, there's a real tendency to leak from the high pressure to the low pressure. There are seals that have to be maintained and clearances that you want to try to keep in range. But over time, lots of things can deteriorate. In addition to this, air heaters are prone to pluggage. And again, if you look at the path of airflow, if you start to plug an air heater, it would tend to force more of the FD fan over to the ID fan gas side. So let's first just understand the gas passes through the air heater. So we have hot gas going in and cooler gas coming out. And then we have cool air coming in, going in the opposite direction usually, and hot air coming out of the air heater. There's 2 basic types of air heater, a tubular and a regenerative or plate type. We're mostly going to be covering the plate type. That's the more common ones. If you do have a tubular air heater, we're looking at the same things, but your design leakage is probably a low number, probably less than 5% design leakage on a tubular air heater, which is why, again, if you get some leakage or holes in your air heater, looking at the actual leakage versus the design values will help you understand if you need to do maintenance. So the hot gases are coming from the furnace, and they go through the air heater, and then they're being usually withdrawn by the induced or ID fan, and then the FD fan is supplying the airflow for going into the air heater, and after it's heated up, it tends to go to the wind box or the pulverizers wherever it's needed. In the regenerative type air heater, we have rotating plates, and so the plates get hot in the gas side and rotate to the air side, and then they're cooled off by the cool air flow. If you have significant amounts of the cool air leaking over to the gas side, you do not cool those plates effectively, and therefore you lose efficiency. So the tendency is for the FD fan air, instead of going to the boiler, to leak over to the ID fan side without even going to the boiler and not recovering the heat from that flue gas. It just lowers the temperature by dilution. And there's other paths of leakage where the actual gases or air go around the air heater and never enter into the heat transfer area of the air heater. Just like we needed the excess air value to look at airflows, we're going to be using the excess air value for different flue gases, and then we can compare, based on how much excess air is in there, how much air has leaked into a flue gas. So we'll be using that equation 20.9 divided by 20.9 minus DO2. And that way we can calculate the excess air in almost any flue gas situation. One of the things I want to be cautious about is that if I'm using control room oxygen values, they might be influenced by potential leakage prior to those O2 probes. So any sort of expansion joint or penthouse leak might actually influence the excess oxygen reading, therefore making the instrumentation think that it has enough excess air left over in the flue gas. Also, those oxygen probes tend not to be 100% coverage of the duct, or in other words, we want like a 9 or 16 point coverage of the duct so that we can get the values of oxygen throughout that whole ductwork. In many cases, the O2 probes are up near the ceiling, put in this way, and they don't cover the whole duct. If you take a portable oxygen probe, and this was my life as a performance engineer, if you take a portable oxygen probe up there with a long enough lance where you can reach down into the duct and go through several different ports across the duct, you'll get a nice grid work of what the oxygen looks like in that ductwork. You can also, with that portable oxygen measurement device, sometimes get values for CO2, carbon monoxide, NOx, and SO2. So if while you're doing your ductwork you find the nitrous oxides are high when the oxygen is low, and then you go over here and the oxygen values are high but the nitrous oxides are low, that doesn't make very much sense from the combustion standpoint, so potentially there's leakage of air diluting that nitrous oxide value. So these portable oxygen instruments, and we don't go into a lot in this class, but this is where you're going to get your better oxygen values both before and after the air heater. You've seen this table before. I'm just basically showing you the oxygen levels and the corresponding excess air. We typically run around 3% oxygen, so typically we're running around 17 or 1.17 excess air. I just wanted to talk about efficiency a little bit, and I'm not going to go into detail about coal quality impacts of an efficiency. We're primarily looking after what is the exit gas temperature of the power plant or the air heater gas out temperature. But because there's cold air leaking in, we'll actually have to correct or make a corrected flue gas exit gas temperature. So in this summary slide of the heat loss method, you can see the heat in the flue gas down there towards the bottom. That's what we're doing or talking about when we look at the temperature of the gas coming out of the boiler. We can calculate the air in versus the gas out temperatures and look at how much heat is getting carried away in that flue gas. So there's a variety of things you need to do a boiler efficiency test, and I'm suggesting that besides the coal and some readings in the control room, you're going to need your air heater leakage. We have to make that calculation to correct the exit gas temperature for the amount of cool air leaking in. There's an easy to use calculation for air heater leakage. It's basically the difference of the high O2 and the low O2, or the exit gas and the entering gas, that high O2 minus the low O2, and then you divide that by 20 minus the high O2. So a fair question to ask is, what is the air heater leakage when I have 3% oxygen going into the air heater and 6% oxygen in the flue gas exiting the air heater? Putting those two values of 6% and 3% into the equation, I can readily calculate an air heater leakage of 18%. And that's what I'll need, is that air heater leakage in percent leakage to make my adjustment on the flue gas exit gas temperature. A more fundamental way to look at air heater leakage is to calculate the excess air values for the 3% value and the 6% excess oxygen values. If I simply take the ratio of 1.4, the 6%, divided by the 1.17, the 3% oxygen, I get a 1.20 value, which says there's 20% air heater leakage. If I use my 90% engineering sort of calculation value, that's what that 90 up there does in that previous calculation, you can see that I can get that same 18% air heater leakage. So the influence on the exit gas temperature on boiler efficiency is quite direct. The hotter the temperatures of the gases, the lower the efficiency. This is a straight line function, and so when I look at the slope, I can calculate that for every about 37 degrees F, I get a 1% change in boiler efficiency. But the problem is in the control room, we look at the flue gas temperature, and it might actually read 300 degrees. And what I'm suggesting is that when that air heater leakage increases, you are actually diluting a higher exit gas temperature down to the 300 degrees. So I made this chart to look at, okay, what is my actual temperature or my corrected gas temperature based on my air heater leakage? And you can see how there's a very significant change from around the design numbers of 10, 12% leakage. When I start getting up around 20 or 25% leakage, I'm incurring quite a significant heat rate or boiler efficiency penalty. Here's how we're going to look at how do we calculate that corrected flue gas exit gas temperature. Here's our equation for calculating what's the actual corrected flue gas temperature. So we take our base gas out temperature, and then we're going to add to that the air heater leakage percent times the difference between the gas out and air in. So that temperature difference between gas out and air in times the air heater leakage divided by 100 to get rid of the percent gives us how much temperature we actually have to add to the situation. If I fill values in at like 300 degrees exit gas temperature and 100 degrees air in temperature, you can see that with 18% air heater leakage, I have to add 36 degrees to my actual flue gas temperature measured to get my corrected number. And remember, that 36 degrees I'm adding in represents about 1% boiler efficiency, or 1% of your annual coal utilization. Now, because the design numbers are typically around 10, I'm suggesting that if you operate around 20, you're going to have about a 0.5%. To spend $100 million on coal, that 0.5% represents $500,000 of additional fuel needed because the air heater performance was not where you wanted it to be. There's a lot of other degradatory impacts that air heater leakage can have on things like precipitators and scrubbers, because that air leakage into the flue gas gives more volume to the flue gas than what it needs to be. And all these things like precipitators and baghouses and scrubbers are all designed to treat a certain volume or have a certain amount of residence time in the vessel. And when we put too much volume in there, particularly because of leakage, then we decrease the efficiency of all those pollution control equipments. Thank you. I wanted to try to keep this chapter short so we could at least know how to calculate it. The hard part, of course, is to actually go out and use your portable O2 probes and probe that ductwork and get actual oxygen values before and after the air heater.